A radioactive sample contains atoms that will spontaneously decay, and the activity of a radioactivity is the rate of decay. That is the number of disintegrations per unit time. The SI unit of activity is the becquerel, in short BQ, where 1 becquerel is 1 decay per second. So if we have a sample that has an activity of 2 becquerel, then on average 2 nuclei will decay per second. And if the activity is 4 becquerel, then on average every second 4 nuclei will decay. So the question here is which is not radioactive, and the answer is actually they all are. So the Earth itself is a source of terrestrial radiation. Radioactive materials, including uranium, thorium and radium, exist naturally in soil and rock. Besides nicotine, tar and other toxins, tobacco contains radioactive heavy metals such as lead and polonium. All organic matter, that includes plants and animals, contains radioactive carbon and potassium, and bananas in particular are rich in potassium. Essentially all air contains radon, which is responsible for most of the doses that we receive each year from natural background sources here on Earth. And then all people have internal radiation, mainly from radioactive potassium-40 and carbon-14 inside our bodies from birth, and therefore we are all sources of exposure to others. All of these sources of radiation add up to about 20 to 50 counts per minute, which is called the background count. This background count is all the ionizing radiation, alpha, beta and gamma particles that are emitted during radioactive decay, that is constantly present in the environment. When we are doing experiments on radioactivity, when we want to find out the activity of a given sample, we will have to subtract this background count from the measurements we take. You may understand that the more particles we have in a radioactive sample, the higher the activity it has. The activity is proportional to the number of radioactive nuclei present in a sample. The proportionality constant is called the decay constant, indicated by the Greek letter lambda, where A equals to lambda times n. And the decay constant is defined as the probability per unit time that a nucleus decays. And since the unit of activity is per second, the unit of the decay constant is also per second. Who wrote this? As it turns out, the number of radioactive nuclei in a sample drops exponentially with time. And when we plot the number of radioactive nuclei in a sample as a function of time, the gradient at any time is the activity of the sample at that time. Now, since the activity of a sample is proportional to the number of radioactive nuclei in a sample, the activity of a radioactive sample also drops off exponentially with time. Note that we may not detect all particles that are emitted by a sample because the particles may not go towards our detector, or in some cases they may go straight through our detector. However, as the particles are randomly emitted in all directions, it makes sense that the number of particles we detect per unit time is proportional to the activity of the radioactive sample. Hence, the number of particles we detect per unit time, the count rate, is also exponential in time. Now, an interesting and very common parameter that is used in relation to radioactivity is called the half-life. We can define the half-life in two different but equivalent ways in terms of the number of radioactive particles in a sample or in terms of the activity. So the half-life of a radioactive nuclide is the average time taken for half the original number of nuclei in a sample of the radioactive nuclide to decay. Or alternatively, the half-life of a radioactive nuclide is the average time taken for the activity of a sample of radioactive nuclide to halve. So if we look at a sample of radioactive nuclides, after one half-life, only half the original number of nuclei in the sample will be left. After two half-lives, half of the remaining nuclei have decayed, So after 2 half-lives, we only have a quarter of the original number left. After 3 half-lives, we have only 1/8 of the original number of radioactive nuclei left, and so on. This allows us to find the relative number of nuclei left after any amount of time. So also after a quarter of a half-life or 7.3 half-lives. It also allows us to answer questions such as how long will it take until 90% of my initial number of radioactive nuclei have decayed? And I only have 10% left. The half-life is related to the decay constant in this way. The half-life is equal to ln2 divided by the decay constant. And since the activity is proportional to the number of radioactive nuclei and the count rate is proportional to the activity, we can apply these formulae to all three parameters. You may have noticed that we mentioned that the half-life was defined in terms of averages. The reason for this is that radioactivity is a spontaneous and random process. When we say that radioactivity is spontaneous, we mean that we cannot speed up or slow down the process. We cannot affect the activity of a radioactive sample. When we say radioactivity is random, we mean that we do not know which nucleus will decay first or when exactly the next nucleus is going to decay. Hence, in practice, our data may not show such smooth curves as shown previously, but the count rate may fluctuate considerably, where the general trend of the process is still exponential.